Okay, so we're going to do H10J.2, and this video may take a few parts, so that's okay. So sit back and relax, and let's talk about this. I'm going to scratch out these y values here because we are only concerned about the shape. Okay, so something that I think that will help us might be to make a sign diagram. So, um, so my first derivative deals with slope, right? So my slope at -3 is 0. My slope at 0 is 0. And my slope at 2 is 0. So I'm going to have these points on my sign diagram: -3, 0, and 2. Okay, so for values less than -3, you can see it's going down. We have a negative slope. For slopes between -3 and 0, we know it's going up. So my slope is positive. And then between 0 and 2, we have a negative slope, so it's going down. And then greater than 2, the slope is going up. Okay, so whenever we go from a negative slope to a positive slope, we've got a minimum. When we go to a positive slope to a negative slope, we've got a maximum. And we go from a negative slope to a positive slope, we've got another minimum. Okay. So we want to draw the first derivative graph. So if I'm going from a negative slope, so I'm going to use, what did I use in the classwork? Okay. In class the other day I used pink for the first derivative. So if I'm making a graph of the first derivative, we know that at -3 we have the slope graph is going to be 0 because if I'm drawing the derivative here, it goes from negative, then it goes to positive, negative, and positive. So it's 0 and at 2. So my graph of the derivative is 0 at these 3 points because the slope changes from negative to positive to negative to positive. So if the slope is negative, it's going to be below the x-axis. If it's going to positive, it's going to be above the x-axis until I get to here. So it's going to be right there, and then it's going to be below the x-axis because it's going down to here, and then the slope is positive from here on out. Okay, the height of and is not so important. It's just that between here and here, you can see the graph is going up, so that means the derivative is going to be positive above the x-axis. Okay, so this is the graph of the first derivative. Okay. Now we want to graph the second derivative. Let's make a sign diagram for that. So the second derivative has to do with concave. And we have a stationary inflection. Well, we have inflection points. At this point right there and at this point right here, it switches from concave up to concave down. So let's call that, I don't know. You want to call that -2? I don't know. Just for, and then right here, let's call this at 1. So we're looking at the original graph f of x, the black graph, and from here till here, it looks like a smiley face, it looks like a cup. That's concave up. So values less than -2 is concave up. The slope continues to get higher and higher and higher. Then at -2, it's no longer increasing in slope. The slope starts going less and less and less until it gets to there. So here we have concave down, and then the slope starts to increase again until it turns around, and the slope keeps increasing, and then once we have concave up. So concave up, concave down. Okay. So now let's make a graph of the second derivative. Oh shoot! Concave down is supposed to be blue. Oopsie. Sorry. Okay. So now I'm going to make a graph of the second derivative. I'm going to do that in green. Okay. So the second derivative goes from positive to negative at 2. So at this point, or close to 2, whatever, we have a positive the second derivative is positive. Then between -2 and 1, the second derivative is negative because it's below the x-axis, because the original graph is the slope keeps getting less and less, it keeps getting greater and greater and greater. The slope goes from being negative to becoming positive, and then here we have concave up, so it continues to get positive. Okay, so this is the graph of the second derivative. Okay, sometimes you might need to watch this video again to understand this. Also, I've explained this in my other video, H10J.2. You may need to watch this one first, but I should have changed the numbering. Oh well, whatever. So now that we've got our different graphs and we've color-coded it and it's all set, okay, so we've drawn our graphs. First derivative I drew in pink. Second derivative I drew in green. Okay, write down the x-intercepts of the derivative for function for the first function. So the x-intercepts are -3, 0, and 2. Okay, and that's where we have minimums and maximums there. Okay, write down all the values when the first derivative is positive. So the first derivative is positive between -3 and 0. And the first derivative is positive greater than 2. So between -3 and 0, you look at the yellow-blue line, and it's just going up. And then greater than 0, my original function, the yellow line, is just going up. Okay. Okay. At point D of this graph, at point D on this graph, the x-coordinate -0.5. Explain why the second derivative is less than 0. So at -0.5, which is right there, right? Negative 0.5. The second derivative is 0. Okay, so when we look at second derivative, we're talking about concave up and concave down. So at 0.5, you can see it's surrounded by negative blue. So the answer would be, so why is the second derivative less than 0? The second derivative, um, uh, the second derivative at negative 0.5 is negative because it's concave down. Why is it concave down? It's because the slope um, continues to increase. So here the slope is like that, here the slope is like that, the slope is going to become horizontal, the slope keeps getting greater. The slope of the original graph um, gets bigger, becomes more positive. Okay, next question. Here we've got the first derivative. There are two points of inflection on the graph. Write down the x-coordinates of these points. Okay, so inflection points happen when the second derivative is equal to 0. Okay, and um, and that was the thing that we talked about on this handout, that when the second derivative is equal to 0. So to figure out, oh, and they've already given you the first derivative function. Okay, so, because this is f prime, isn't it? Okay, so we need to find the second derivative. So we get negative 72x squared plus 18x plus 3. Okay, we want to find out when the second derivative is equal to 0. We can see that we can factor out a negative 3, and then we get 24x squared minus 6x minus 1. And I think, oh, can I factor this? No, I can't. So we want to make this equal to 0. So to figure out how to make that equal to 0, I'm going to hit y equals on my graphing calculator. Okay, and let's type in my equation. Um, 24x squared minus 6x minus 1. I can graph that, and we see it's right there. I'm going to change my window a little bit. X max, let's make it negative 2. No, negative 2. Make that 2. Let's look at that graph. Okay, so I've already done this over here. So we do left bound, right bound, second trace to find our zeros, and we find our two zeros. So these are the x-coordinates. This value here and this value is the x-coordinates of those points. Okay. So we got our graph, and we just said it was x equals negative 0.114 and x equals 0.364. Okay. Okay, and what did we do? We typed in the equation y equals 24x squared minus 6x minus 1, and we did second trace, and we picked 2 for zeros, and then we did the left bound, right bound, yes, and we hit enter for each of those guys to get our zeros. Okay, so let g of x be the second derivative. Explain why the graph has no inflection points. Okay, so g of x is equal to the second derivative. So my second derivative is negative 72x squared plus 18x plus 3. Okay, so I've got g of x, which is this function that we just got up here. So explain why this graph here doesn't have an inflection point. So to figure out inflection points, we need to make the second derivative equal to 0. So we're trying to find when the second derivative of g of x equals 0 to show that g of x, this graph here, doesn't have an inflection point. Okay, so the first derivative of g of x is equal to negative 144x plus 18, and the second derivative of g of x is equal to negative 144. Okay, so we found the second derivative of g of x. G of x we know is this, and so why does it have no inflection point? Because the second derivative of g of x is never equal to 0. Okay, so therefore the second derivative of g of x has no inflection points. Okay, because to have an inflection point, the second derivative has to be 0. Okay. Okay. So, okay, here we've got a function, and we want to find out the gradient of the normal slope when x equals pi. Okay. So, so we want to find the normal. Okay. So we need to figure out the slope. So we need to find the first derivative. Okay. And using this, we're going to have to use the product rule. And the product rule says that if I've got the derivative of x is going to be equal to u times v prime plus v times u prime, prime, and where f of x equals u times v. Okay, and then here is our product rule formula. So in this equation, I have u equals e to the x. I have v equals cosine x. The derivative of u is equal to e to the x. The derivative of v equals negative sine x. So now using this formula, I'm going to say, okay, so u, which is e to the x, times v prime, which is negative sine x, plus v, which is cosine x, times u prime, which is e to the x. And So that's my derivative. And now we want to plug in pi in place of x. So then I get e to the pi times negative sine pi plus cosine pi times e to the pi. Okay, so I just replaced x with pi. Okay, now what is sine of pi? In case you forgot your unit circle, just type in sine pi, right? We know sine of pi is 0. Cosine of pi is um, is 1. Did I do something wrong here? Cosine of pi is negative 1. Duh. Okay. E to the pi. Okay, so I replace cosine pi with negative 1, replace sine of pi with 0. And so, of course, that cancels out, and then I have the first derivative when x equals pi is equal to negative e to the pi. So this is the slope when x equals pi. So that means the normal slope is going to be the opposite sign and the reciprocal. So it's going to be positive and 1 over this. So remember, it's the reciprocal and opposite sign. The normal slope is the reciprocal and opposite sign. Okay, let's look at the next question 4, and then I'm going to have lunch after that. Okay, so consider we've got a function here, part of the graph. There's a maximum at m and a point of inflection at n. So find the first derivative. So we know the first derivative of this function, 3 times 1/3 is going to be, we're just going to have, it's going to be 1, so I've got x squared. The first derivative of that is going to give me 4x. First derivative of negative 5x is going to be minus 5. Okay, find the coordinates of m. Okay, so this happens when the first derivative is equal to 0 at that point. When the first derivative equals 0, then we're going to have m. So we're going to make the first derivative equal 0. 0 equals x squared plus 4x minus 5. So making that equal to 0, I can factor this out. And to get 5, we're going to have 5 times 1. This one's going to be plus, this one's going to be minus. And then now that we've factored it out, we know that x equals -5 and x equals +1. And at -5, this looks like it's going to be -5. This looks like it's going to be 1. So our maximum is going to be, oh, the x-coordinate of the maximum is -5. Okay. Find the x-coordinate of n. Okay, so n is an inflection point. And inflection points happen when the second derivative equals 0. Okay. So let's make that second derivative equal to 0. So here we've got the first derivative is x squared plus 4x minus 5. My second derivative is going to be equal to 2x plus 4. So we want to make that second derivative equal to 0. Right, we're making that second derivative equal to 0. So then I can subtract 4 on both sides. And then I get x equals -2 if I divide both sides by 2. So that is the x-coordinate here at -2. Okay. Let's highlight that green. Okay. The line L is tangent to the curve at 3, 12. Okay. Find the equation of this line. Okay, so 3, 12, that's like over here somewhere, right? Okay. So, to find this equation, we need the slope. So first, find the slope. So at x equals 3. So I'm going to use the first derivative and plug 3 into that equation. So I'm going to have 3 squared plus 4 times 3 minus 5, and that's going to give me the slope when x equals 3. So then I end up with 9 plus 12 minus 5, and so my slope is equal to 16. Okay, so now I want to find my equation in this form. So y minus y1 equals m, x minus x1. I've got my slope, and I've got my y minus 12 equals 16 times x minus 3. I'm plugging in the y of 12 and the x of 3, and then I get y equals 12. Sorry, y minus 12 equals 16x minus 3 times 16, which is 48. Okay, and now I'm going to add 12 on both sides. And negative 48 plus 12 is going to give me negative 36. So I have y equals 16x minus 36. And that is the line tangent to the curve at that point in this form. Okay. The next 2 pages I will do on the part 2 of the video.